To run a model with the reasoning power of DeepSeek v3, you now pay less than 15 cents for every million input tokens. That pricing model breaks the math of traditional dense architectures. It is only possible because of the extreme sparsity found in mixture of experts, or MOE, models. While MOE drastically reduces the active parameters required for each token, it shifts the system bottleneck. The limitation is no longer pure compute power. It is the bandwidth of the high-bandwidth memory, physically loading those parameters onto the chip. Because HBM bandwidth dictates the physical ceiling of the hardware, maximizing the efficiency of every gigabyte transferred directly determines the profitability of these high-volume APIs. The industry standard for accelerating these memory-bound models is speculative decoding. The mechanics rely on a two-step process. A small, efficient draft model proposes a tree of candidate tokens, and the large target model verifies all of those candidates in parallel. The standard heuristic for engineers is straightforward. Drafting larger and deeper trees of candidate tokens produces higher parallel verification throughput. This graph plots inference speedup against draft tree size. Dense models show a continuous upward trajectory. But with state-of-the-art speculative decoding in an MOE model, the scaling breaks. Speedup peaks at a 31-token tree, then actively degrades. A recent paper titled MoE-Spec isolates this physical bottleneck. The researchers introduce a training-free fix that reclaims up to a 30% throughput gain. Accelerating sparse models requires moving past the scaling laws that govern dense architectures. The failure point lies in the verification phase, stemming from the difference between dense and sparse architectures. In a dense model, verifying a massive 60-token graph tree is highly efficient. The system requires exactly one full load of the model weights into the GPU to process the batch. This diagram shows a 63-token draft tree in an MOE model, mapping chaotically to distinct experts. To verify this, the target model must load the mathematical union of all selected experts across the tree, creating an expert explosion. As unique experts approach the layer's total, the system loses the benefits of sparse activation entirely, completely saturating the high-bandwidth memory. By using large draft trees, we force the MOE to temporarily revert back into a dense model, maxing out bandwidth and destroying the speedup. The solution requires looking past the total volume of activated experts and examining their specific activation probabilities. This chart plots expert rank against probability share for a 63-token tree. Expert routing follows a heavy-tailed distribution. Just 32 experts capture an overwhelming 93% of routing probability. The remaining 32 form a long tail, capturing a mere 7%. These straggler experts might serve only one or two candidate tokens in the entire batch, yet they consume the exact same memory bandwidth to load as the most vital, heavily used experts. Precious memory bandwidth is being wasted on statistical outliers. This presents a massive opportunity for aggressive algorithmic pruning during verification. The researchers built a verification time expert budgeting algorithm to address this, called MoE-Spec. The system begins with router-based ranking, summing routing probabilities for each expert, sorting them in descending order. It then enforces a strict budget limit. Capping the budget at 32, it loads the top-scoring shortlist and entirely drops the long tail. What happens to a drafted token whose naturally preferred expert was just deleted? The solution is a substitution policy. The routing vector dynamically reallocates its selection, routing strictly to the next highest scoring experts available within the surviving budget. This elegantly preserves the token's hidden state, while strictly capping the hardware memory cost of the batch. We can now evaluate the physical impact of this budget on hardware saturation when dealing with massively deep draft trees. This scatter plot plots speedup against active experts. At tree size 255, standard Eagle 3 loads 54 experts. Bandwidth saturates, dropping speedup. MoE-Spec, however, hits a hard budget wall at 32 experts. The data point locks immovably against this wall, climbing vertically to a 2.1x speedup. Because the actual acceptance rate of the drafted tokens barely drops, only a 1.4% reduction, these massive speedup gains are purely a result of eliminating the HBM loading overhead. MoE-Spec transforms the historically unpredictable memory cost of speculative decoding into a mathematically bounded, predictable hardware guarantee. This expert budget hyperparameter provides inference engineers with a dynamic dial, allowing them to actively balance latency against accuracy based on specific application needs. This graph of reconstruction error versus expert budget highlights a lingering inefficiency. Treating expert probabilities independently wastes budget on experts that frequently co-activate and provide redundant outputs. There is a 25% efficiency gap between the current router method and the mathematically ideal Oracle curve. The immediate future of this research lies in designing selection algorithms that predict these co-activation patterns. This will push expert budgets even lower without requiring full model execution. As the industry shifts toward ultra-sparse models to minimize inference costs, decoupling verification memory from draft complexity becomes a structural necessity for continued scaling.